Faraday's law. Actually, use that. We wrote magnetic flux as B. So this means magnetic flux. The B means magnetic. So there are two expressions, actually one general expression. One, if the magnetic field is uniform through some loop or area or surface, I'll just say surface, then the magnetic flux, just the total amount of magnetic field that goes through it, is given by the magnetic field, whose flux you're calculating, dotted with the area vector for that surface. The area vector is taken perpendicularly to the plane of the surface. Which means that if you have, for example, a loop sort of like this, and the area of it, the area vector is like this, so that it's perpendicular to the plane of the loop, and maybe there is a magnetic field that goes through this thing. So this is B, right? Notice that if this loop, what I'm trying to draw is a loop like this, at an angle, and there's a magnetic field going that way to the right. If this loop is horizontal, the area vector is vertically upward, and it will be at 90 degrees to the magnetic field, and the cosine of 90 degrees is 0, so that means that there would not be any flux through the loop. So by putting the dot product over here, right, which means the magnitude of the magnetic field times the magnitude vector times the magnitude of the area vector times the cosine of the angle between the magnetic field and the area vector, that's theta, then we can call this the magnetic flux through the loop. Now, what would happen if this magnetic field through this loop is not uniform? Maybe the magnetic field here through the loop is different in magnitude from the magnetic field here and from the magnetic field here. It's different in magnitudes. In that case, you can't just say B times the area, because B is not the same throughout the entire area of the loop. So in the more general case, what you have to do is then you integrate. So if B is not uniform, the magnetic flux would be given by, you have to take like an infinitesimal area dA dotted with the magnetic field, and then do the integral over the area. Notice that if the magnetic field is uniform, you can put it outside the integrand, and then it would be B dotted with the integral of the area, but the integral of the area is just the area. Right? So this is really a special case, and this is a more general case of magnetic flux. So, I guess I wrote it over there. Okay. Magnetic flux would have units of a magnetic field, which is in Tesla, multiplied by an area, which is meter squared. So the unit of magnetic flux is Tesla meter squared. And magnetic flux is a scalar quantity, not a vector quantity. Notice that it has to be a scalar quantity because it is the result of multiplying two vectors via the dot product. And when you multiply two vectors using the dot product, what you get is a scalar quantity. So this magnetic flux, which is in Tesla meter squared, is a scalar quantity. And 1 Tesla multiplied by meter squared is defined as a Weber. That's somebody's last name. So you can say the magnetic flux to this loop is 5 Weber, or you can say the magnetic flux to this loop is 5 Tesla meters squared. So the Weber is the unit of magnetic flux in the metric system. It's just the amount of magnetic field that goes through some surface of area A. So Faraday discovered in 1831, what Faraday said was that if this quantity, magnetic flux, if this quantity through a surface, a loop, changes for whatever reason, if it changes, then there will be a voltage induced in the loop. And that voltage is going to then give rise to a current in the loop. So the voltage that shows up when this magnetic flux is changing, that voltage is called the induced voltage. It's an induced voltage, induced by the change in the flux, in the magnetic flux. And the resulting current is called the induced current. Now, that induced voltage is also called the EMF, induced, the induced EMF, induced voltage. If you want to quantify the current, you just use Ohm's law. See, the induced voltage will be the induced current times the resistance of the loop, right? So you just use that. Oftentimes this induced voltage is written as EMF, like that. So if you want to know what the induced current is in a loop induced by a changing magnetic flux, it will be equal to the voltage that's induced divided by the resistance of the loop. The question is, how can we write this induced EMF? And that is what Faraday contributed. Faraday's law says that the induced EMF is equal to the negative of the derivative of the magnetic flux with respect to time. And it is also equal to, we can also write it in terms of something else, but I'm going to wait for that before I write that expression down. For now, let's focus on the negative of the derivative of the magnetic flux with respect to time. Notice that given this expression, right, this induced voltage will exist only while the flux is changing, the magnetic flux is changing. Only while the magnetic flux is changing will there be a voltage induced in the whatever it is that the magnetic flux is changing, right? It could be a loop, it could be a coil. Right? Remember last time I brought a coil and I put a magnet in there and I just let it sit there. So there was a magnetic flux through the coil, but it wasn't changing. And because it wasn't changing, it was just fixed at so many Webers. The induced current was 0 because the induced voltage was 0. But as soon as I pulled it out or brought it closer to it, as I was pulling it out or putting it in, the magnetic flux was changing, and during that time there was an induced voltage that then gave rise to a current, and then you saw that as a deflection in a needle in the galvanometer. So there are two things that I want to do. I want to do a problem, an example where we calculate this and we calculate that. But I want to say something about this minus sign. This minus sign could be interpreted using, so it's a very important minus sign, what's called Lenz's law. So there are three laws that we discuss in this chapter. I mean, we say something about Ohm's law, which we learned in another chapter. We say, we talk about Faraday's law. And there's a minus sign in Faraday's law that you write mathematically. And you can explain that by talking about Lenz's law. So let me talk about Lenz's law, and then I'll do an example. Okay? Let me talk about Lenz's law. But first, we need to remember something from chapter 28.
Excuse me, Professor. Could I just a quick question? So magnetic flux is basically just the amount of magnetic field through one area, like an area.
Yeah, like for example, if I want to know the magnetic flux through this loop, it's the amount of magnetic field going through the loop.
Okay.
If I want to know the magnetic flux through the door, then it's the amount of magnetic field that goes through it.
Okay. Thank you.
That's how I like to think of it. Yeah?
Yeah. Makes sense.
And you'll see various examples where we have to calculate magnetic flux. But before I discuss Lenz's law, we need to review something from chapter 28. Okay, so I'll just say, all right. So the question that I want to ask you is this. What if I have a loop like this? And, a loop like this. And what if there is a current in this loop? Maybe there's a little battery in there that's, there's a current in it, right? Suppose that current is in the counterclockwise sense. Suppose the current in this loop is in the counterclockwise sense. So here's a question that I have for you. What is the direction? I don't care about the magnitude, just the direction of the magnetic field that is produced by this current in this loop in this area. Let's just say near the middle. Or in this region over here. What is the direction of the magnetic field generated by that current in that loop? Which way? Out of the board. Good. So the magnetic field there would be out of the board. Okay? Out. And then we can talk about the magnitude and so on, right? Actually, we only calculated the magnitude of that magnetic field at the center of the ring, right? What if we have a loop like this instead? And suppose the current is this way. What is the direction of the magnetic field generated by that current in this region?
Into the board.
Into the board, right? You just actually use the right-hand rule and you just say like this. So that'll be into. And what if we have a loop like this? And the current is like that. What about the direction of the magnetic field over here?
Out of the board. Oh, wait.
Out? Yes? Okay, so that wasn't really a review. You already knew that. That's the end of the review. We're good with that? Just use your right hand. If the current is in the counterclockwise sense, the magnetic field that it will produce is out of the board. If it's clockwise, it's into the board. If it's just a different shape, it's counterclockwise. In this region, it's going to be out of the board. Okay? All right, good. No more review. So this, let me talk about Lenz's law. Okay. There are many questions in many situations, but it's all based on Lenz's law, that one could ask. So pay attention. So you can do it like that. Okay? And I'll use a silly analogy, but if it helps, hey, who cares? So what if I have a ring like this? In other words, there's no battery attached to it, right? There's no current in it. There's that. Or like this. All I have over here is just a connector, to connect this end of this coaxial cable to the other end. This is not something that generates a voltage and then leads to a current in the loop. It's just a connector, right? So I just have a ring with no battery, no power supply connected. A ring. In fact, this is probably even better. All right. And so my discussion right now is on Lenz's law. Right? I want to talk about the meaning of that minus sign. I want to focus on that, right, for a little while. So we have this loop like this. And this loop is in the presence of a magnetic field, right, generated by a Bohr magnet. Suppose this is the north end of the Bohr magnet, and I put it like this. So this is the north end, and this is the loop. What will be the direction of the magnetic field through the loop generated by the Bohr magnet? And this is the north end. Which way is the magnetic field pointing?
Towards us? North end?
That's N. This is N.
That's
This is south. So N, like this. In fact, let me try to draw this. Maybe this will be better. If you have a loop like this, in fact, I don't care which way the loop is. If I have a magnet like this, what is the direction of the magnet? Let's forget about this. What is the direction of the magnetic field generated by the magnet?
Doesn't it come out of
Out,
north?
which way?
Out of north and into south?
Out of the north into the south. So it's going to come out like this, right? So over here is like this. It's like that, right? So if I put the loop over here, with the north side of the magnet close to it, what is the direction of the magnetic field going through this loop? It will be to the right. And if I put it like this is the north over here, it would be
Into the board?
into the board. Yes? Yes? Into the board, right? So if I put the magnet like this with the north end over here, then the magnetic field will be into the board. So let's say that given the position and the strength of the magnet, only given the position of it, there are 5 magnetic field lines coming into. So this is B due to the magnet, right? How about I call it a magnet like this? And that X means into the board. Suppose that I hold this ring like this, and I grab this magnet and I hold it like that. Is there a magnetic flux through the ring? Yes or no?
No. Or wait, yes.
Is there a magnetic flux through the ring?
Yes.
Yes, there are magnetic field lines going through it, right? So there's going to be a magnetic flux. Is it changing?
No.
No. Because it is not changing, there's not going to be a current in this loop. Right? Only when it changes. Only when the magnetic flux changes will there be an induced voltage. And if there's an induced voltage, there's going to be an induced current. And R will be the resistance of the ring. But if I hold the magnet at a fixed position and I don't do anything to the ring, there is a magnetic flux through this ring. There's an amount of magnetic field going through the ring, but it's not changing. And because it isn't changing, there's no voltage induced in the ring. And how about we say that the ring is happy? like that, and the ring is happy. The ring says, oh, that guy is holding that magnet at some distance away from me, and the ring talking. And the way it is right now, there are 5 magnetic field lines going through me. 1, 2, 3, 4, 5. And it's the same value, 5, 5, 5, 5. I'm happy. It's happy. Happy because there's no voltage induced in it. Because if the magnetic flux is a constant, the derivative of a constant with respect to time is going to be, or the derivative of a constant is 0, right? So if this is 0, there's no induced voltage, there's no current in the ring. Yes? Now, what if I do something to this magnet? What if, which one would you like me to move it? Towards or away?
Towards.
Towards. Did you say towards? What if I move it towards the loop? As I move it towards the loop, do you think the magnetic flux through the loop is going to increase or decrease?
Increase.
Increase, right? In the previous picture, I had something like this. This was N, this was S. You have magnetic field like this, right? If I have the ring over here, maybe this one goes through, but this one misses it, and this one misses it, right? But if I bring the magnet closer to the ring, I may be able to capture, more magnetic field lines going through it. So as I hold the magnet here, as I hold the ring over there like that, and I grab the magnet and I move it closer and closer and closer, there's going to be more and more and more magnetic flux to this ring. And then the ring is unhappy. The ring says, oh, my magnetic flux is not constant. Ooh, I'm unhappy. I want it to be constant, because when it's constant, I'm happy. But that guy is moving that thing in front of me, and he is, making the magnetic flux through the ring bigger, 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 bigger. So the ring says, okay, I had 5 magnetic field lines going through me. Now this guy is bringing in the magnet, and now there's a 6th magnetic field line coming in. And there's a 7th magnetic field line coming in as I move the magnet closer. The magnet says, no, I was happy with 5. Now I got 6, and now I got 7, I want it to stay the same. So what the ring then does, what it does is says, okay, let's call the soldiers here. So let's call the free electrons. You guys can run, right, around the group, around the ring. The free electrons, right, they can go around. And they have a meeting, and they say, okay, I was happy with 5 magnetic field lines going through me. That guy is changing it, making it 6, making it 7, making it 8, making it 9. And we don't like that. We want it to stay the same. How about we keep it at 5 as soon as it begins to move the magnet? So then they say, okay, the electrons can then run around, the free electrons, 1 electron per atom, let's say if it's copper. The free electrons can run around the ring to make up a current. And what happens if the ring has a current in it? It'll produce a magnetic field. And the ring knows about vectors. It says, oh, magnetic field, I had 5 coming through. If as soon as he increased the external magnetic field to 6, the ring wants to create its own magnetic field out. That would be a magnetic field produced by the induced current in the ring, so that it is out to cancel the extra 1 that showed up because I moved the magnet closer. And as I keep moving the magnet, another magnetic field line, this is an external magnetic field due to the magnet, right? And then the ring says, no, we gotta cancel that. So it's gonna be out. So now you tell me, what would have to be the direction of the current in this ring induced by the changing magnetic flux if it has to produce its own magnetic field out of the board? Which way? Counterclockwise. So as soon as I move the magnet in, there's going to be an induced current showing up in the counterclockwise sense to oppose the change in the flux, to oppose it. That's why mathematically, how do you write down mathematically an expression that will lead to that behavior that the ring is opposing the change in the flux? Well, opposing mathematically means put a minus sign in there. And the induced voltage over here, the EMF that's induced, or if you like, you can call it delta V induced. By Faraday's law, it will be in magnitude equal to the derivative of the magnetic flux with respect to time. You know, the change in it. The minus sign is just there to tell you something about the, in which direction ultimately the induced current is going to be in the ring. Like, if you like, you can call it like this, just the absolute value of it, right? And then the induced current is going to be just that EMF divided by the resistance of the ring. So Ohm's law will tell you the magnitude of the induced current as it relates to the induced voltage. But Faraday's law will tell you what that induced voltage is going to be. What if instead, let's do this again. I had the ring like this, right? No wires connected to it. And I held the magnet at some distance in front of the ring. And again, I had 5 magnetic field lines going through the ring. There was a magnetic flux due to the external magnetic field that the magnet generates, right? And this is into, right? Now, what if instead of me grabbing that magnet and moving it closer and closer to the ring, what if instead I just hold it there? If I just hold it there, the ring is happy, there's no current in the ring. But if I pull the magnet away so that it goes further and further away, what's going to happen to this magnetic field, to this magnetic flux? Is it going to get bigger or smaller?
It's smaller.
So it's like it loses this one, right? And if I keep pulling it, it's going to lose that one. It went from 5 to 4 to 3, and then the ring says, wait a minute, you're changing my flux, I'm unhappy. So then the ring says, I have to then do something to keep the flux at what it was when I was happy. I want to keep it at 5. So now the ring has to then, the ring then gives, generates a current that will produce a magnetic field due to the ring due to the current in the ring that will make up for the lost magnetic field because I'm moving the magnet away from it. So this would be the induced magnetic field, which would have to be into the board. So now you tell me, in this case, what will be the direction of the current around that ring if it has to produce a magnetic field directed into the loop? Clockwise. So now in this case, the current is going to be this way. And again, the rate at which that magnetic flux is changing will give you the EMF and take that voltage, that induced voltage, that EMF divided by the resistance of the ring, and that'll tell you how many amps that's going to be. And if I stop moving the magnet so that we have a new constant flux, magnetic flux through the ring, that current is going to go to 0. That current exists only for as long as the magnetic flux is changing, only while it is changing. If I stop changing it, then it goes to 0. And depending on, if you remember the demo, right, I pulled the magnet in, out, in, out. When I put it in, there was a deflection maybe this way in the needle, in the galvanometer. When I pulled it out, it was the other way. Because the current, was going in different directions depending on whether the magnetic flux was increasing or decreasing. Yes?
Does the speed that the magnet moves, does that change at all? As well as like the radius?
So for example, you'll see, The voltage induced, which is going to lead to a bigger current, right? The voltage induced depends on how quickly the flux is changing. The more quickly the flux changes, which would be like if I move the magnet in faster, you know, then depending on how quickly I change the flux, then yes, the speed will give rise to a bigger induced voltage, which will give rise to a bigger current. The resistance of the ring is fixed, right, by the ring. But yes.